All right, so thank you for joining us today for the Oasis Sales Did You Know webinar series. Today's is on thermal simulation that's available in the PADS Flow, and Richard Ozaki is online. He's our mentor graphics AE that specializes in these tools, and he will be conducting the presentation and demonstration through the presentation. But I just have a few slides here we're going to go through real quick, and then we'll let Richard take over and get started. So for those that haven't heard of Oasis Sales, we are a complete electronic and mechanical engineering solutions provider for Mentor Graphics, or Siemens now, as people may or may not know. Siemens purchased Mentor Graphics earlier this year. So we offer complete electrical design, simulation, analysis, and obviously the complete flow that we have can assist in cost savings with doing simulation. And Richard's going to drive that one home here with since this is a simulation product. Oasis Sales has been a partner with Mentor Graphics and now Siemens for over 16 years. We were established in the late 1980s as a Mentor Graphics model sim reseller, and then when Mentor bought the PADS or Innovata company, we became the electrical reseller as well, and now we're also doing all the MCAD tools from Siemens. So a complete solution from beginning to end can be provided from one vendor now. So our technical team that's available for you for assistance when you're evaluating tools or have questions about any of the products that we sell, Kyle Lake, who's located in the Portland area, and myself, Brett Klingforth, our AEs for all of the products that we sell. We also get assistance from Mentor Graphics AEs in certain areas, like in this case, Richard specializes in all the thermal tools. Just so you know, our salespeople in the area, Derek Pop is up in the Northwest, Lizzie Marsh is kind of the Midwest, Andy Bowe is also Midwest territory. Hopefully you've met some of these people if you're a customer of ours. If not, these will be some of the people that you talk to as you work with us on looking at the tools and when you buy. And then Pete Archelios in the Texas area, Oklahoma, Rick Truza, more of the Northeast, and then Jason Johnson is also in our upper Northwest territory. And then we have an inside sales team as well, Fawn Chang and Dennis Reynolds. You may have spoke with these people in the past as well, or worked with them. Come on, advance to the next slide. Just for general help, you can contact us at sales@oasissales.com or email Fawn, and the appropriate person will get back with you. Just a couple details. If you're asking questions since you've been muted, please use the chat window in the bottom of the GoToMeeting control panel off to your right side there. If you have a question, type that in. We'll answer most questions towards the end of the webinar, unless it's pertinent to what we're currently talking about during the session. And then lastly, past Did You Knows can be found on our website. So you can go to oasissales.com, Oasis Events, or just go to oasissales.com, click on Events. These are the 5 that we've done already. This one will show up here in a couple days as well. If you want to watch it again or have some, send it to some of your friends at your companies. So let's go ahead and get started. I'm going to turn the presentation over to Richard, and I'm going to let him introduce himself here. I got to find Richard in the list. There you are.
All right.
All
okay.
right.
Thank you very much, Brent. So I'll
welcome.
take it from here. So today we're going to be talking about FloTHERM XT for PADS. FloTHERM is a thermal analysis tool which allows you to solve for conduction, convection, and radiation coupled with fluid flow, and the technology is called CFD, or Computational Fluid Dynamics. My name is Richard Ozaki. I'm an application engineer for Mentor Graphics, or Siemens PLM as it is now, and I assist the Oasis guys in promoting our software within the US. So what is FloTherm XT? Well, as I just kind of alluded to, it's a 3D thermal simulation software using CFD technology. It will allow you to solve for all three modes of heat transfer, including airflow patterns. It will allow you to read in ECAD data from PADS, combine that with MCAD data from, for instance, SolidWorks or Creo, put everything together in an assembly and understand how everything's going to work in terms of the heat transfer. So we're going to see some automated PCB transfer from PADS. This is an easy to use and non-expert tool. We're really focusing on ease of use and productivity, right? So you don't have to be an expert in this tool to be able to use it. It's designed to be easy to pick up and put down for engineers that wear multiple hats and perform multiple roles. So why perform thermal in the first place? Well, the real return on investment comes down to three main points. The first one is reducing the prototyping and testing. Okay, so the costs associated with tooling prototypes, checking to see if heat sinks are going to work. You know, maybe if it doesn't, you're going to have another one tooled up. How many respins do you go through till you get it right? We're really trying to reduce that cost. The second one is reducing the time to market. So if you're doing less prototyping and less testing, then you're going to be able to get your product out into the market faster and, you know, jump some of your competitors possibly. And yes, you can reduce the engineering and the lab costs associated with that as well. And finally, if you have done a lot of virtual testing, then you're going to end up with more of an optimized and reliable design. So your product is less likely to fail in the field. You're going to have less warranty returns. You know, your product will be cheaper to manufacture. Maybe you're over-engineering things rather than under-engineering. So there are various things that we can check for with a thermal compliance tool such as FloTherm to ensure that your product's going to operate safely, reliably, and save you costs in the design phase. So when it comes to electronics cooling, what's actually going on? Well, there's two main hard temperatures within electronics cooling, a min and a max. Typically, the maximum temperature is what we call the junction temperature within the package, and this is around 120 degrees C or 260 degrees Fahrenheit. After this temperature, commercial chips tend to fail. They will burn themselves out, and obviously the logic won't work anymore, and then you've typically got a dead product. On the other end of the scale, you've got the ambient, which you need to dump all that heat to, and you know, upper scale for an ambient maybe about 50 degrees C, so about 130 degrees Fahrenheit, and that would be modeling, for example, a hot summer day in Arizona or Saudi Arabia. Your iPhone needs to be able to work in Phoenix just as it will do in Alaska. So there's a broad temperature range that your electronics product has to operate in. And the heat's going to travel out from the chip towards the ambient, going through various obstructions. Okay, so that chip is probably placed on a board. That board probably has some thermal features in there, such as thermal vias or copper pores or heat sinks. Okay, that board might be one of many within a telecoms backplane system, for example, and that might have fans or baffles or items to guide airflow. And then that server system might be one of many within the data center, and then finally you're going to be dumping all that heat out towards the ambient. So there's various levels of thermal analyses that you can perform, and FloTherm can handle all of these different analysis types within the base package. And how easily the heat finds its way out will determine how hot you're going to end up at the junction over here within your package. So the lower the junction temperature, the more reliable your product is going to be. So what's the workflow going to look like today? Well, we're first going to be pulling in some of our geometry from PADS, i.e. our PCB that's been designed and routed. We're then going to import some of the mechanical assemblies. So maybe from your mechanical team, you'll be requesting things like heat sinks and fans and enclosures. We'll be putting that all together, and then we need to apply, for example, materials, heat loads, fans and heat sinks. We're going to be talking about meshing. Okay, then we're going to be solving the equations, the CFD solver. We're going to analyze the results, and then we're going to make design changes to optimize the solution. So typical design changes you might want to make would be, for example, different heatsink configurations, or maybe you need to move to liquid cooling, or maybe you need to try different gap pads, maybe you need to use a phase change material. So all of these what if questions can be answered by performing a CFD analysis on your electronics up front before you've committed to tooling and signed off on the product. So let's jump straight into it. I'm going to share my screen and let's just have a look over here. So my starting point is going to be pads. This is the example that I had up on the screen just a moment ago. It's a fully routed board, so you can see it's going to have 6 layers. All the components are laid out, positioned, routed. All the copper pores are done. So this is kind of a end stage PCB that's kind of been at the sign-off stage. You don't have to use FlowTherm at this stage. You can use it earlier when maybe the board shape and the components have just been placed, but the board is unrouted. You can perform a thermal analysis there, but you're not going to get the detailed copper, explicit copper definition within the PCB if you do so. Okay. So we do support this, but this is PADS VX, the latest version from Mentor Graphics, and the way we access FlowTherm XT is to go to the Tools, Analysis, and then FlowTherm XT option. And what that's going to do is that's going to push all of this information over into FlowTherm XT for us automatically. Okay, so let's do that now. You can see we get the splash screen for PADS FloTHERM XT, and I'm going to give my project a name to start with. So let's just call this Oasis 2, and we're going to be looking at an empty project for now because we're going to be defining all of our mechanical assembly constraints. I choose my unit system, so I can choose the US unit system, and that will put all my temperatures in Fahrenheit, or I can use the SI project that I'm going to be looking at. So if you are looking at a sealed box, a sealed enclosure, you might want to perform an internal only analysis. But because we're looking at airflow around my PCB and inside and out, we're going to be doing an internal and external analysis. We want flow and heat transfer. Here's my ambient temperature, 35 degrees C. That's about 95 degrees Fahrenheit. Okay, we also need to set a gravitational direction. So for natural convection purposes, we need to set gravity in a certain direction. And what we'll see is as the components heat up, the air will also heat up, it will become less dense, and it will move up and away due to gravity, buoyancy effects, and then cooler air will be dragged in from underneath. So defining gravity will determine the natural convection direction. We can also have a look at thermal radiation. So this is going to be conduction, convection, and radiation. And we can also look at a steady state or a transient analysis. My working fluid is going to be air. Now remember, fluids don't have to be just gases. They can also be liquids. So if you want to look at things like liquid cooled cold plates, we can certainly do that as well using FlowTherm XT. My default solid is going to be aluminum, so basically everything in the model is going to be assumed to be aluminum unless we say otherwise. And I click finish, and what this will do is this will build a base project for me into which I can then start to pull in my board, my mechanical assembly, and go from there. So I'm going to click OK to import my board. And the first thing we're presented with is what we call the Flow EDA bridge. Now this is a dedicated part of FlowTherm XT which allows you to prepare and then import the PCB for moving over into the thermal analysis tool. And you can see we've got the board here. I've got all the stack up information. So for example, here's my top layer. I've got the thickness in ounces. I've got the percentage coverage of copper on this particular layer, and I've got that for all the layers. So here's this is a 6-layer board. Here's layer 2. If I look at the VDD plane, you can see it's majority of it is copper, 70%. If I look at these layers, we can check the layers, check the routing on each of the layers. We also have the components on the screen, so you can see if I expand this, I have components. A lot of them are filtered out at the moment, so if you can see if I bring them back and look at the board, you can see various resistors, capacitors, all small passive components, crystals, passive components which we don't necessarily need for the analysis but are already on there. So that's really where the filter components option comes in very useful. Right? So you can see by turning on and off the filter, components will come in and out of the view. And I'm going to turn on a few more filters now just to filter out some parts that I don't want. So I don't want connectors. So over here I'm going to put in, if my reference designator contains a certain letter, I'm going to filter those out. So connectors are typically denoted with P. I don't want LEDs. I don't want crystals. Okay, so just by putting those in and filtering those out, you can now see that those have been taken out the analysis. And also I don't want any small components, so anything less than 10 millimeters in length, I want those filtered out as well. So just for demo purposes, I'm going to be pretty harsh and just strip out most of the parts and leave me with just the main components that I'm interested in. Okay, these are my three main chips over here. So the next thing I want to do is define the power dissipations on each of the components. So you can see down here that each of them have got 0 watts. Now if I wanted to, I could put in a certain steady state power dissipation on these packages. So for example, I've got one here. This is my main power component. Let's dissipate 12 watts on this guy. I can put on 5 watts on this guy over here, and you can see that will give me the power dissipations for the components. Alternatively, if you have a large number of components, we have the option to import a power list. So a power list will in one shot apply all of the powers to basically give the thermal dissipations onto the components. So let's come over here to FloTHERM XT for PADS. Oops, wrong one. And over here I have something called a corporate powers CSV. And if I just edit that, all I'm going to have, it's on my other screen, is the reference designator, comma, number. Okay, so in one hit that's going to basically put all the powers onto my components for me. So you can see down towards the end I've got U100's got 10 watts, for example, U11's got 25, so this is very, very high. So if I apply that now, you can see this has got 3 watts, 10 watts, 0.5 watts, so we can see all the various component power dissipations. The next thing you might want to do is add a little bit more detail onto the component modeling. So they're modeled as simple blocks at the moment, which is fine for low power components, but if you have datasheet information for high power components, then you can enter these into FloTHERM XT. So for example, this is a FPGA device from Altera, and if you come down in the list, you'll find θJC and θJB, junction to case, junction to board thermal resistance values. Okay, so this determines internal resistances within the package from the junction to the case, junction to the board, and tells you roughly what the delta T per degree per watt is going to be for between the junction and the case temperatures. So because the θJC is lower, this tells me that the heat is designed to go up into the case and away by a heat sink, and this number is higher, so less heat is designed to go down into the board. And we can do that. We can apply those numbers over here. So we change this from a simple to a 2 resistor component, and then I can give my θJB 4.19 and θJC 0.36 into the model, and that's going to model my FPGA in just a little bit more detail. Another thing we can do is actually swap out components with library items. So for example, this is going to be a PQFP, plastic quad flat pack device, and I have a detailed model in my library. So if I swap that out now, what we're going to see on the screen is a more detailed representation of that particular package. You can see with the outline, it's got the leads, it's got the die in the center, it's got the lead frame and the bond wires. That's a fully detailed package. And this guy over here is actually a BGA. This is a BGA with a center. There isn't balls in the center, but you can see now a better representation of the BGA. So if you do have these components, companies like Intel, Xilinx, AMD, they will provide FloTHERM models on their website. If you have them, then you can certainly swap them out very easily over here in the Flow EDA bridge. And at this stage, I'm ready to actually push this over into FloTherm XT. So let's do that now. And what it's going to do is going to build for me it's going to go from the PADS file, which is effectively a 2D file format, into a 3D mechanical assembly with all of that detailed information that I just defined earlier. So it's going to have the board information with all the copper stack up in there, and it's going to have the components modeled in higher fidelity. It's going to have all the thermal power dissipations, and yeah, we've just gone from the PADS file to a more detailed thermal simulation model, which we'll look at very, very shortly. So it's just creating that now, and it's going to push that over into FloTherm XT for me. Okay, we're almost there, so 91%. So the more components you have, the longer this will take, but the reason it's taking so long is, again, we're going into 3D here. So let's just place that down inside our assembly, and you'll notice that we have this black box around our geometry. And this is what we call the computational domain around the geometry. So this is the amount of world that we're modeling in our analysis, and you can see it's much too big at the moment. So what we're going to do is we're going to tighten that up a little bit. Let's just go plain white again. Okay, so if I zoom in, you can see here's my board, my components on there. It's only got the components that I left in there. If I zoom into my BGA, for example, you can see here's the balls underneath the package. This is a bare die package. We're going to be placing a heatsink straight onto here. But let's just sort out this computational domain first of all. So here we have the overall domain. Let's edit this in view. I'm just going to pull this down, get this into roughly the right location, something like that. Okay, so we're tightening up the domain in this direction as well, something like that. And if I wanted to, I could solve this right now. And because I've set a gravity in the negative y direction, what would happen is the heated air would move up and away, and we'll get a certain temperature. But as we're dissipating such high powers, this will almost certainly fail due to temperature related issues. So we need to cool this down with a mechanical construction enclosure around it. So to pull in a construction, a mechanical assembly, let's insert a component. I'm going to hit Browse. And this is where it pays a little bit to know a little bit about mechanical CAD software. But let's just pull this in. And let's pull in, sorry, no, wrong one. PADS XT enclosure. Okay, so you can see here's my enclosure. I'm free to place it wherever I wish in the domain, but what I'm going to do is I'm going to choose my origin, plot my origin onto the screen, and if I mouse over that, that's going to fix that into the right position for me. Okay, so I'm just going to mouse over, click that into position, and that will then have my enclosure around my PCB. So let's have a little look at inside what's going on. Let's look at it from the back side first of all. So one thing you'll notice in this model is that we have a blower. Okay, so we're going to be forcing air across my two hot components with heat sinks, and we are going to then be forcing out the slots. So another thing you'll notice is that we have a couple of guide vanes here, so the airflow is going to be guided over the heat sinks. So by default, air always wants to take the path of least resistance, so by putting in some guides we can get the air to where we want it, and hopefully it'll be more effective at actually cooling the components down. So let's just bring back my board like that, and we can see what the airflow looks like. If we have a look at the blower, over here we have a, where we are, here we are, we have a blower. And again, I'm going to refer back to a data sheet for this particular blower. Let's come back over here. to this guy here. This is a blower from Pabst, I believe, EBM Pabst, correct. So I've got the mechanical construction, I've got some information about the airflow that it can provide. That's the 12.9 CFM, that's the rated flow. I've got the voltage that it runs at, and most critically, I have the fan curve. So this graph here shows us the pressure head versus flow rate that this particular blower can generate. And this will depend on how much resistance there is downstream, fluidic resistance there is downstream to the airflow. So the air having to fight through heat sinks, having to go through vents, this is all going to be causing a pressure drop and a back pressure onto the fan, and depending on what back pressure the fan sees, it's going to blow at a certain rate on this particular curve. So we can use this information directly in FloTherm XT, and if I come into my flow device and look at my fan curve, you can see that we've imported this already from that datasheet, and you can import this as a CSV file as needed to model this particular fan. The other thing we have are some heat sinks. So if we have a look at this, the first heat sink, so both of these, in fact, both of these heat sinks, I believe, have the same material on here. Yep, aluminum 6061. That's a fairly typical aluminum for heat sinks. And in between them, let me just spin this around and zoom around like this. I don't know if you can see that. Well, you can definitely see it now. There's this blue item here, which is our thermal interface material. So a thermal interface material, like a gap pad, will bridge the gap, fill in all the little roughnesses on the surface of the package and the heatsink, and give you better heat conduction. And again, it's critical that you have the correct material properties on there. So I have here a thermal interface material, 3 watts per meter Kelvin, and again, this is the sort of information that you can get from data sheets. For example, here's a 3M thermally conductive tape, and if you come down a little bit down here, you'll be able to get the thermal conductivity of that particular thermal pad or thermal tape. And you can see it's 0.9, so this is a fairly low performance one, but you can use this information directly in FloTherm XT. All right. So once you've built your mechanical assembly and your PCB, you've defined materials and components, you define fans, the only last thing you need to do is actually solve this model. So let's come over to the thermal analysis tab. We're going to be generating a mesh. I'll touch on meshing a little bit later, but when we look at the results, but we can add additional mesh onto certain components, such as I have on the bracket, and you can see a little icon here. We can then solve, and in terms of solving, we can choose as many CPUs as we wish for the actual solving process. The software is multi-core by default. So what I'm going to do is I'm going to jump over to another model which I've already got solved, and we can have a look first of all at, let's have a look at the mesh in the model. So let's just show this. I'm going to just hide this. This isn't the mesh. What we're looking at is the flow speed. So let's just show the mesh on the model as well. So as I kind of touched on, the mesh is largely automatic. You can define additional grid on certain components if you wish, but it's largely automatic. It's intelligent enough to know when there's narrow channels and heat sinks and areas that require additional mesh to resolve, such as, for example, the slots in between the outlet over here. And you can see it's Cartesian in nature, and it cuts the geometry out of the mesh and applies the mesh accordingly. So here we can see the flow speed. Let me just flick back to temperature, and what we're going to see is the temperature profile. It's just calculating that now. We can see the temperature profile, and let me just change my units. Temperature, let's change that to degrees Fahrenheit. And we can see that we have an ambient of 95 and a maximum temperature somewhere at 228. So if I just set this for the plot, you can see the air temperature around my package is around 204 degrees, okay? And we can probe the plot, we can mouse over anywhere in the model, and understand exactly what the temperature at the mouse location is going to be. Okay, so you can see air temperatures over here. There's a little bit of leakage, 130 degrees, 124 degrees. We can see some leakage over here. So we can use cut planes in the model, 2D slices through the model to understand what the temperature is at that particular plane in the model. That's the Z direction. We can also have a look in the X direction. Nope, not that way. Just hide that. Okay, so we can see, again, we got the mesh on here, we can see the air being heated and being forced along that way. All right, and next, let's have a look at the actual PCB temperature. So by plotting the PCB temperature, we can get an understanding of what the temperatures of the components are going to be. So you can see this component up here, this is getting way too hot, 232 degrees C. Maybe this is a voltage regulator or a power amp or something like that that's dissipating a lot of heat on the edge of the board. It's not in the airstream, which is not ideal, so that's why it's getting so hot out over here. So we might want to move this into the airstream or away from the edge of the board, and that will keep that nice and cool for you. We can also have a look at heatsink temperatures. So if we have a look at just the single heatsink, we can have a look at what the delta T range on the heatsink is going to be. So between 174 and 206, we can see the coolest fin is in the top right, where it's in the direct path of the air, and the hottest fin is in the center above the hot spot of the component, as you might expect. Okay, we can also plot the heat transfer coefficient if you wish. So the heat transfer coefficient drives the airflow, the heat transfer into the airflow. And you can see again in the top right, the most heat transfer is occurring over there because it's in the direct path of the coolest air. Okay, let's just go back to solid temperature. Where are we? Over here. Okay, and if we also wish, we can track to see what the airflow through the model looks like. So by plotting flow trajectories, we can virtually see how the air moves through the model. So you can see it being pulled into the blower. It's being accelerated around. It is then being passed over the heatsink. We can see it going in through the heatsink fins. We can see it coming out of the vents on the back. So by animating the particles, we can get an idea of if there's any leakage. So you can see there's a little bit of leakage here coming at the bottom of the connector. There's some leakage coming out the back of the board as well through these slots over here. So the airflow really gives us an idea of where the air is going, and a little bit too much is bypassing this heatsink for my liking. There's not enough going through the center of the core of the heatsink, and that's why it's maybe got a hot spot in the middle there. Okay, so we can also have a look at numerical results. So for example, we can look at convergence information. This particular model takes about 30 minutes or so to solve, and we can see what the pressure differential is across the fan. If I change my goal type to a volume, we can see each of the component temperatures. Let me just get rid of this. So we can see U102, U104. I can click through the components and see what the final steady state temperature is going to be. Okay, so you can see 154 Fahrenheit. If I come down and let's sort by value. So you can see my U12, this guy up here, is getting the hottest at 232, and the next one is 194. So really we need to do something about this guy to get him cooled down. Okay, and then finally, if you wished, you can generate a report. I can generate a report based on the goals that I've created. So the goals are the component temperatures. In fact, let's just take a quick screenshot. I can go next, my Mentor Graphics logo, and let's dump that out into a PDF document, and that will generate a document for me now with all of the reports for me. Okay, so all the information that I went through about the setup. I have all my component temperatures. There's my problematic guy here, and Just maximize that. And towards the end, we have all the convergence information with the graphs. And if you want to put any screenshots in, you can do it as well, like this. And you can automate the report generation process if wished to customize it for your particular company. After that, you can perform a parametric study where you can vary things. So you can vary components, you can vary materials, blowers, PCB layouts, right? So the parametric study will allow you to take advantage of the base case by trying different scenarios and different instances of the model. So that was just a very, very brief overview of FloTherm XT. Just to have a look at some typical results back in the PowerPoint, we can see we have cross planes through the model looking at temperatures. We can also create some surface plots looking at component temperatures and PCB temperatures and the min and max values. We can look at heatsink temperatures and understand where the coolest, where the hottest, where the most effective heat transfer is into the air. We can also animate things, as I showed you just a moment ago. So we can have a look at dynamic airflow analysis. And what are the types of customers that use FloTherm XT, common applications, we can look at package level models, so companies like Intel, AMD, onsemi, Xilinx, they will all use FloTherm for package level thermal analysis. We can also go up to mobile devices such as tablets, phones, look at more of a single PCB within a natural convection enclosure. Consumer electronics, again things like PCs and graphics cards, medical devices, telecoms equipment, and LED lighting is becoming more and more prevalent with there being a requirement to keep the junction temperatures of the LEDs as cool as possible. So I guess the main things that people want to know when they do thermal analysis would be things like junction temperature prediction. You want to know what the airflow looks like. Is your heatsink in the right place, or is the airflow doing what you want it to be doing? Heatsink sizing and selection is an important one. Fan sizing and placement, and finally PCB placement and thermal optimization. So looking at thermal vias, copper pores, thicknesses of the layers within the board to try and pull the heat out of the components. Just a couple of success stories. FloTherm XT is used at Visteon for automotive dashboard cooling analysis. So as cars become more and more complex, there's more and more heat dissipation within them, and Visteon are using it very successfully to keep their electronics cool over the lifetime of a car, which can be anything up to 25 plus years. ECUs, again another automotive example. So Visteon use FloTherm XT for ECU cooling, so engine management, but also braking systems, comfort systems, in-car entertainment systems. These all have their own ECUs, and again needing to keep those reliable over the full 25 years of operation requires some analysis to ensure that reliable operation. And finally, the Microsoft Surface 4 was actually designed with FloTherm XT. You can see in these images we have some heat pipes and some blowers and a PCB needing to keep these cool, keep this tablet cool in a variety of orientations and usage scenarios and angles. FloTherm XT was used to validate thermally to ensure that the product was going to be reliable over the entire lifetime of the tablet, which is much less than the car, typically less than 5 years, something like this. But I'll say thank you very much for attending the meeting, and if you have any questions, please feel free to contact Oasis Sales. Let me just put up the final information again. You can contact Oasis here, sales@oasissales.com, or Fawn, who is who looks after the inside sales. And if you want a custom demonstration or an eval, please let her know, and we can take care of that for you.
Hey Richard, this is Kyle Lake. I can just really quickly finish this off here. So recap. Thanks again, Richard. And I don't see any questions in the chat dialog box. So if you guys do have questions, feel free to, again, contact us at sales@oasissales.com or that number for Pat or for Fawn Chang. Just a quick recap. Richard did a good job showing what FloTherm XT is capable of, and we just believe that it's a good tool to use for managing your thermal issues across the entire design, not just board level, but for your entire design for electronics. Help avoid unexpected circuit behavior and just help validate that your circuit's going to be operating correctly. We are available to offer out evaluations for this tool, so if you are interested in trying out this tool to see if it'll work well for your applications, please feel free to reach out to us. We can help you out through the process of installing the tool and actually simulating some of your electronic design. All right, with that, I think we'll end the session. Again, thank you for attending, and thank you, Richard. Have a good rest of your day.
Bye, everyone.